In this tutorial, we will be discussing the periodic trends. You may have noticed several things as we're studying chemistry. For instance, the alkali metals, such as sodium, form a +1 ion, while the fluorine tends to form a -1, as well as the other halogens. Some elements are metals and others are nonmetals. Noble gases are chemically inert, which means that they typically don't react, while the alkali metals are chemically reactive. They react quite violently with water. The chemical properties of elements are largely determined by the number of valence electrons they contain. So valence electrons are the outermost electrons. You may remember doing the electron configurations. For instance, if we look at calcium, which has an atomic number of 20, and if it's neutral, that means it also has 20 electrons. 1s2, 2s2, 2p6, 3s2, so that's 10, 12, 3p6, 4s2. 4s2 is the outermost because the principal quantum number is the highest, and that's what we're going to be looking for, because those are the outermost electrons. Those are the ones who are actually reacting. All the other ones are called core electrons. Their properties vary in periodic fashion because the number of valence electrons occur in periodic fashion. So calculations show that the atoms with 8 valence electrons, or 2 for helium, are predicted to be particularly low in energy and therefore stable. So if we look here, the valence electrons always end, with the exception of helium, in 8. That's because S can hold 2 electrons and P can hold 6 electrons. These are the noble gases. The noble gases are chemically stable and thus relatively inert or non-reactive, as accounted for by the quantum model, because those energy levels are filled. Elements with electron configurations close to the noble gases are the most reactive. For instance, the halogens are right next to it, or the alkali metals are on the other side, but if they just lost 1 electron, they can go the other direction and be like a noble gas. This is because they can attain the noble gas electron configurations by losing or gaining a very small number of electrons. So let's look at the alkali metals. That's in the very first row. They're among the most reactive since our electron configuration is ns1. They all have 1 electron in the valence electrons. If they lose that 1 electron, they can go to the other side of the periodic table and be like the noble gases. For instance, here, if they lose 1 valence electron, sodium could be like neon. Here, if potassium loses 1 electron, the potassium could be like argon. If they can react to lose an electron, they attain the noble gas configuration, which explains why the first group tend to be +1 cations. Alkaline earth metals, which is the second row, all have electron configurations that end in s2. So that means there's 2 electrons in their valence shell. In their reactions, they tend to lose 2 electrons to form a 2+ ions. For the same reason, they want to be like the noble gases. For here, calcium, if it loses 2 electrons, could be like argon. If magnesium loses 2 electrons, it could be like neon. But they're not as reactive as the alkali metals because they have to lose more. The halogens are the row right next to that inert gases, the noble gases. N2, S2, P5 for a total of 7. And remember, they're trying to get to 8. So if they gain just 1 more electron, it could be like the noble gases. So chlorine could gain 1 electron and have the same electron configuration as argon. That is why they tend to have a -1 charge, because they just want to add 1 more electron. So here's the pattern. These in row 8 are the noble gases. They're inert because their shells are full. So they all end in S2P6. Here's the halogens. If they gain just one electron, they could be like it. So that's why they're all -1. Oxygen, sulfur, selenium, so on, need to gain 2, and nitrogen needs to gain 3. The other side of the table, lithium can lose 1. Sodium could lose 1. Calcium could lose 2. That's why it's a +1 and +2 charges. Alright, so let's talk about other trends that you see on the periodic table, because as things fall into place, other things occur. For instance, the size of the atom. Surprisingly enough, the atom actually gets smaller as you go from left to right. Remember that the atomic size of the atom is determined by the distance between the outermost electrons and the nucleus itself. So we're talking about the radius. The reason why it's getting smaller, the size of the orbital depends on the principal quantum number. These all have the same principal quantum number. These all end in 2s. These all end in 3s. And so on and so forth. With each step across a period from left to right, the number of protons in the nucleus is increasing, yet the principal shell is staying the same. So that means that there's going to be greater protons to attract those electrons being the same distance out, which means that they're going to be able to pull tighter and tighter and tighter. This increase in the number of protons results in a greater pull of the electrons from the nucleus, causing their size to actually decrease. So even though the numbers are going up from left to right, the size is going down because of the fact that there's more protons in there to pull on them. The other factor that determines the size is how many shells out there are. As you move down the column in the periodic table, the atomic size increases. As you move down the column in the periodic table, the highest quantum number increases. So those shells, so if here's the nucleus, those shells are getting further and further out. Unlike the previous example where it was staying within the same shell. Since the size of the orbital is increasing with the increasing principal quantum number, the electrons that occupy the outermost orbitals are farther from the nucleus as you move down the column. So as you move down the column, the atomic size increases. As you move down the column of the periodic table, the highest principal quantum number then increases. So 1, 2, 3, 4, we're getting further and further out. So we can summarize this. Since the size of an orbital increases with an increasing principal quantum number, the electrons that occupy the outermost orbitals are farther away from the nucleus as you move down from the orbital. So here's a summary of it. I actually tried to reorganize the summary by saying that notice how the upper right hand corner is the smallest. So as you move to the upper right hand corner, the atoms are getting smaller. From left to right, because they're in the same quantum energy shell, and it's just getting pulled in tighter. And from top to bottom, from bottom to top, it's getting smaller because how far away is getting smaller from the center. So this actually affects like ionization energy and other factors as well. So ionization energy increases as you move to the right across the periodic table and decreases as you move to the left. So the further away the electrons are from the center of the atom, the nucleus, the lower the ionization energy. So it decreases as you move away from the upper right. So it decreases as you move to the lower left. That's because the electrons are getting further and further and further away from the nucleus, and so therefore there's less of a pull to gather more electrons. Ionization energy is the amount of energy it takes to lose an electron. And if the electron is far away, it's hard to keep a hold of it. Alright, so let's look at metallic character. Metals versus nonmetals. Once again, as you get further away from that upper right hand corner, as you go down to the left, you're becoming more metal. So this is more metal. Because this is the difference between whether you want to gain electrons or lose electrons. Metals tend to want to lose electrons, while nonmetals tend to want to gain. So therefore, as you get further away from the nucleus, you're going to be more and more willing to lose an electron. As you move across the period in a periodic table, ionization energy increases, which means the electrons are less likely to be lost in a chemical reaction. So let's think about that for a minute. As you move across a period, from left to right, the ionization energy increases, meaning that it's going to take more and more energy for it to lose an electron, which means it's less likely to lose an electron in a chemical reaction. Metallic character decreases as you move to the right across a period and increases as you move down. Because remember, metallic character is whether or not you want to lose or gain electrons. Metals tend to lose electrons. So the less energy it takes to remove an electron, the more metallic it's going to be. And that is your summary of periodic trends.